uh, yeah, to the lecture. But one more time, you can collaborate, but for the project, you can work in group, but individual submission. Everybody has to send his own work. Now let's go back to the notes, today's notes. So we are going to continue where we've left last time. Last time we've defined what we defined, we've calculated, we found a way of calculating the inverse of a matrix. We've learned the basic row operations. We've defined what a elementary matrix was. It was a matrix that allows us to perform the row operations. Now we're going to dive deeper into the concepts.
Excuse me, sir.
Yes,
Before we continue, I would like to know if you received my assignments.
yes, I'll receive all the assignments.
Okay, thank you, sir.
So diagonal and triangular matrices. So if a n by n matrix A is said to be upper triangular if the if aij equals to 0 when I is greater than j, and lower triangular um, ai if the aij entry are all equal to 0 when I is less than j. So A is said to be triangular if it's either upper triangular or lower triangular. I think it's better to see it when it's on paper, to actually understand it when it's on paper. What we mean by upper triangular and lower triangular. So you have a matrix like this. Um, so you have something like this. Here you have 0, 0, 0. So it's like this is 0, 0, 0. This is like a value. This is like value, 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 um, and another value over here. Okay. In that particular case, you can see that this is your I entry, I. This is your row, and then this is like your J entry. This is your column, and you notice that yes, this looks like kind of like a triangle. Okay, this kind of looks like a triangle, and you notice that here I equals to 1, I equals to 2, I equals to 3. Here j equals to 1, equals to 2, and then j equals to 3. Now we say that when I is greater than j, you have aij equals to 0. When I here equals to 2, meaning I greater than j, the entry equals to 0. When I equals to 3, it's greater than j, which is equal to 1, the entry equals to 0. When I equals to 3, the entry j equals to 2, I greater than j, the entry equals to 0. When you have a case like this, we say that your matrix is upper triangular. Upper triangular. And now when you have, so you can see that your triangle is kind of like up here. Now when you have a matrix like this, when for the ij entry, when I is for every entry such that I less than j, the ij entry equals to 0. And that is a case like this where you have entries here, and the entries here, entry here, entry here, entry here, and yeah, entries in here, yeah, here. But here you have like 0, here you have 0, here you have a 0, We call this type of, you can see that you have a triangle over here, something like that. So this is like a triangle that is like placed like lower. But here you can see that the triangle is raised up like this. So this is a lower triangular matrix. Okay. So let's look at the entries. So here you have j equals to 1, j equals to 2, j equals to 3, I equals to 1, I equals to 2, I equals to 3. So when j is greater than I, you have 0. J greater than I, you have 0. So when j equals to 3, I equals to 1, j is greater than I, right? So it's a 0. J is equal to 3, I equals to 2, it's 0. So we can see example of that. This is like a general kind of example, but let's look at more precise example. Let's say you have a 3 by 3 matrix. The 3 by 3 matrices, you have 3, you have 0, you have 0, you have 2, you have 2 here, you have 0 over here, you have 1, you have 1, and you have 5. Okay, so you have a 3 by 3 matrix, and you have another matrix like this one: 1, 6, 1, 0, 0, and 4, and 0, 0, and 3. Now you can notice something here. You have kind of like a triangle. Okay, the triangle is up there, and then you have a kind of like a triangle over here too. Okay, so here we can see that this is I equals to 1, I equals to 2, I equals to 3, j equals to 1, j equals to 2, j equals to 3. You can see that when I is greater than j, the entry ij equals to 0. So I is equal to 2, j is equal to 1. We can see that the entry is equal to 0, I equals to 3, j equals to 1, 0, I equals to 3, j equals to 2, 0. Okay, so in that particular case, we are dealing with a lower upper triangular matrix. Upper triangular matrix. And here we are dealing with a um, lower triangular matrix. As we can see, the ij entry are all equal to 0 when when j is greater than I. J greater than I, we obtain aij entries equal to 0. Here we are dealing with a lower triangular matrix. Okay. Now, we say that the matrix is diagonal when it's at the same time, if it's um, at the same time upper and lower triangular. So it's like a matrix is diagonal if the ij entry is equal to 0 whenever I is not equal to j. So let's look at this. You have a, we call this type of matrix diagonal. So let's see examples of diagonal matrices. Let's say you have something like this.
Excuse me, sir.
Yes.
Can you show your previous paper, please?
Oh, good.
Just a second. Okay, thank you, sir.
So now regarding diagonal matrices, we said that a n by n, n by n matrices, a matrix is diagonal if aij equals to 0 whenever I is not equal to j. And now let's look at example of these. You have, for instance, a matrix like this one, 1, 2. So I here equals to 1, j equals to 1. You have a value. I equals to 1, j equals to 1, you have a value. But other than that, all the other values are zeros. Another matrix, you have 1 here, you have a 3 here, you have a 1 over here. And everything else is 0. Like it's only the values in the diagonal that are not equal to 0, but everything else is 0. Here you have a 0, 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 0, 0, 0 here. But you can see that in the diagonal you have something, you have a value. This is what we call a diagonal matrix. Another one, you have like 0, 0, 0, 2, 0, 0, 0, 0, 0. Still, it's still a diagonal matrix because this rule is not violated. This rule, the fact that for ij, for whenever I is not equal to j, you have a 0, that rule is not violated. If I had a 6 over here, then the rule would have been violated. But here I have 0 here, 0 here, but it's not important. What is important is the fact that whenever I and j are not equal to 0, you have zeros. Okay, so this is diagonal, this is diagonal, this is diagonal. Okay, so whenever you have something like this pattern, you have this. So a diagonal matrix is both. It is upper and lower triangular. Okay, so that's what makes that particular matrix special. So now we want to try something. Let me go back to the class notes. So any questions related to this? So I was saying, so okay. So diagonal matrix and triangular matrices. The n by n matrix is said to be upper triangular if I equals to ij entry equals to 0 whenever I is greater than j, and the lower is lower triangular if I for any ij entry equaling to 0 when I is less than j. Also, A is said to be triangular if it's either upper triangular or lower triangular. So example of these, we have the 3 by 3 matrices, these ones, and they're both triangular. The first is upper and the second one is lower triangular. Now a triangular matrix may have zeros in the diagonal, just like in here. Here we had a 0 in a diagonal, right? So it may have a 0 in the diagonal. However, a linear system x equals to be in a straight triangular form, the coefficient of the matrix A must be upper triangular with non-zero diagonal entries. So this actually shows you the difference between having a system in a triangular form, in a straight triangular form, uh, to compare it to the triangular, to a triangular matrix. So for a triangular matrix, you can have zeros in a diagonal. But for a linear system, when you write them in a triangular form, like the coefficient matrix must be in such a way that like you should not have zeros in the diagonal. Of if you augment the matrix, if you turn it into a coefficient matrix, you should not have zero in the diagonal. So a n by n matrix A is diagonal if the if you have like a ij entries equaling to 0 whenever I is not equal to j. So here we have the following matrices. You have these matrices, and this is what we've done. And the matrix, a diagonal matrix is both upper and lower triangular. So here we say that all the matrices are diagonal because, as you can see, they have values in the diagonal, and for any entries not equal to the ij, to not for every ij not being equal, we have zeros as entries. So it's a diagonal matrix. Now let's talk about matrix. So before we move on, any questions? So let's move on
Sir,
to, yes,
uh, the three examples that you showed just above.
yes,
Yeah, the last one,
yes.
I is equal to j, but like it's zero.
I equals to j, but it is zero.
Yeah.
Mm-hmm.
And
So that
if
is
I understood well, normally if they are different,
mm-hmm.
that means that they should be like
Zero.
zero.
Yes.
And if they are equal, maybe they should be otherwise.
No, if they are equal, it's irrelevant.
Okay.
It's irrelevant to the definition.
Okay.
Mm-hmm.
Thank you.
So yeah, the fact that they are equal should not impact, does not have any effect. What is important is the fact that whenever I is not equal to j.
Okay.
Mhm.
No problem.
So triangular factorization. It's possible to represent the reduction process in terms of a matrix factorization. So it's like you want to write, you have a matrix and you want to transform that matrix in terms of product of two matrices. So that's what we mean by matrix factorization. So it's possible to represent the reduction process in terms of a matrix factorization. A m by n matrix can be reduced to strict upper triangular form using only row operation 3. So let's see that. So example, let A be a matrix. Let us use only row operation 3 to carry out the reduction process. So let's try to do this one. So what is going to happen here is that we are going to do like a regular row operation, row reduce operation, but with a very small difference. So you have your matrix A with entry 2, 1, and then 4, 4, 5, -1, 2, 2, and then 9. So that's your matrix A. So what we want to do is to use row operation 3, row operation 3 to reduce, to carry the reduction process. Okay. So what's gonna happen is that so let me reduce this one. When I do the reduction, I'm gonna take, my goal is to remove, I'm gonna take this row as my pivotal row, and I'm gonna use that row to eliminate the other rows. I mean the values in the columns, the 1 and 4 here. So this is what I'm gonna get. So I have to do -2 row 1 plus row 2, and -2 row 1 plus row 4. And if I do so, I'm going to get 0 here, 3, 1, 0, -9, and 5. So what I've done is actually doing negative 1 half multiplied by row 1 plus row 2, and I did a -2 row 1 plus row 3. So let's try to do something else. We are going to record the coefficient that we've multiplied by in order to cancel. So for example, to cancel the value over here, one that is here, I've used negative one half. The negative one half is that coefficient, but I've used negative one half into this. In order to get 0 here, I had to multiply the first row by negative one half. So we can notice that this entry over here, this entry here, is located in the second row, the third, and the first column. So let's keep track. Let's track the multiples. So the multiples that we use to cancel this this row, this entry, we're gonna call it L, because it cancel the entry 2 1. Call it L to 1. Okay, now the coefficient that I've used is negative one half. So I have to use a positive version of this one. So it's gonna be plus, so negative one half, that's what I have initially. But here what I'm gonna use specifically is a negative version of it. That's gonna be one half. Next, I've noticed that in order to cancel this entry over here, the entry is located in row 3, column 1, right? So to cancel that entry here, I've used this coefficient over here, these multiples. And that multiples cancel the value that is here. So I'm gonna name that multiple L, row 3, column 1, 3, 1. It's actually negative, but I'm gonna put it as a positive one here. And that's gonna be equal to plus 2. Now the other reduction process will be to do um, is going to be to eliminate. Now I'm going to use this one as a pivotal row, this row over here as my pivotal row, and then I'm going to use that row here to eliminate this value over here. So my goal, I'm using the row reduction process to obtain a lower triangular matrix. That's my goal. So now I want to eliminate the 3 that is here. So what I do is I'm gonna take row 2 multiplied by a negative 3 by plus 3, and then I'll add it to row 3 to eliminate row 3. And let me copy. So 2 0 0 4 2 3 1, and then here I have a 0 and 8 over here. Okay, so this is what I'll use the 3 that is here to eliminate and obtain that value over here. So normally I will call, as you can notice, this entry that has been eliminated is located in row 3, column 2. So I'm going to call this, I'm going to store this multiple in as a row 3, column 2, row 3, column 2, and it's a 3. It's a plus 3. I'm going to just put a negative in front, and that's going to be negative 3. Going to be negative 3. Now, if I'd use, for instance, if my so the way I've done my row reduction, so sometimes people will do row reduction by doing something like 2 1 4 4 5 negative 1 2 2 9. The way they will do the reduction is because here what I do, I multiply one row and then I add it to another row. But others will do, for instance, doing multiplication of one row and then they subtract it from the other row. one half. For example, they will have done for instance something like one half row one minus row two. Done yes one minus row two like this to obtain the same result like 2 0 0 4 2 3 1 -9 and then 5. They will have used one half row one minus row two, and they will have done 2 row one minus row three. Okay, so if you use like if your way of doing the row reduction is to actually taking one row minus another row, if you use the minus sign, you do not need to, when you store your values like 2 1 or 3 1 3 2, you don't need to make it negative because you already used the negative sign when you were calculating. You only take your one half and you plug it directly here, your 2 you plug it directly here. So, but if you're doing the way I do with a plus in the middle, plus in the middle, plus in the middle, you're taking one row and you're adding it to another row, you're not subtracting, then you have to make it negative. That's a methodology of calculation. Okay. So with
So
that being
basically, sir,
yes,
the goal here is to make the coefficients positive.
no, the goal is not to make the coefficient negative positive. The goal is to record the coefficient.
Okay. Okay.
So for example, if I was continuing with this one, I would have done -3 row 2 minus row 1, row 3, negative row 3, so -9 minus row 3, and I have here -3. So here you can like if your way of doing it was using a subtraction, when you record the values, you don't really have to. You copy the values, you copy the coefficient that you've used directly.
Mm.
I think in the class, the person who used this technique that I've noticed with the negative sign here is Asan. I've noticed that he put the negative here. So if he's doing his reduction, if he wants to record the coefficient, he should not make it negative. He has to directly use his coefficient. Okay. Now, if somebody is using this technique with a plus here in the middle, then you have to put directly your values like this, and then you make them negative. Okay. So both technique works, but it depends on what you're using. If you're using the negative sign in the middle here, you don't have to change the thing. But if you're using the positive sign, just like I'm doing, you have to change the sign when you record your coefficient. So we recorded the coefficient.
Okay.
That's the that's the second step. We recorded the coefficient. Now we have when we do the reduction. So we had our matrix A. When we've done the reduction, we have this matrix here in the end, 0 and then 2, 1, and 8. This is the matrix that you obtain in the end. And as you can notice, this is the upper triangular matrix. This is the upper triangular matrix. And we can call that matrix U because it's upper triangular. U like upper. Now the matrix that you obtain, we had the coefficient that we have recorded was L21 one half, L31 equals to 2, and then L32 equals to -3. So we can store these values into a triangular matrix, into a matrix. So L21, so in the L21 entry for that matrix, I'll have to write one half. So you're going to store it in a 3 by 3 matrix. So L21 entry, I put one half, L31 matrix, I put 2. Okay, let me write it down in terms of, yeah, I put 2 over here. and L3 2 I'll put negative 3. I'll call that matrix L. And then in that matrix, I will make all the diagonal 1. I'll in the diagonal, gonna write 1, 1, 1 as diagonal, and every other entry is gonna be 0. So the way I construct this L matrix is to rewrite, I put 1 in the diagonals, and then I copy the stored coefficients L31, L32, and then everything everywhere else is gonna be 0. Okay, so as you can see, this is the upper triangular matrix. This one is a lower triangular matrix. Okay, so the factorization is actually so if we actually do the L matrix multiplied by the U matrix, we will get the matrix A. So for example, if I do 1, 1 half, and then 2, 0, 1, negative 3, 0, 0, 1, multiplied by the U matrix that I found over here, that is, if I do this product, I'll obtain the matrix A, original A matrix that was 2, 1, 4, 4, 5, negative 1, 2, 2, 9. So this is my L matrix, lower triangular. This is my upper triangular matrix. The product is going to be A. Now, this is what we call the LU factorization. LU factorization of your matrix A. So you have your matrix A, and if they ask you to factorize your matrix, we can write it as a product of a lower triangular matrix and the upper triangular matrix. So your matrix M by N matrix can be decomposed into the product of two matrices, being a lower triangular, and the other one being a upper triangular matrix. So and this process is the process that you went through. Like we started the matrix A, and we've reduced the matrix A, and we found the different coefficient. We store those coefficients into a matrix. This process is the factorization process. Okay, so this is the LU factorization of a matrix. So any questions regarding this? Okay, so let's go back to the note. Okay, so we've completed this part. So we had the matrix A, and we use row operation 3 to carry out the reduction process. And when you do that, we record the multiples of the first row that were subtracted in the row reduction process. We have subtracted the coefficient negative 1 half, negative 2, and 3, and we set L21 equals to 1 half, L32 equals to negative 3, and L31 equals to 2. And we are going to insert these values into a lower triangular matrix named L. So the lower triangular matrix that we've created is this one, with a diagonals, with 1 in the diagonals, L21, L31, L32, and then we're going to replace L21 by its value, which is 1 half, L31 by its value, which is 2, L32 by its value is negative 3. So the reduced matrix that we found and that is in the upper triangular form can be denoted as U. So this matrix that is in the upper triangular form that we obtain through reduction process is what we'll be calling our matrix U. Then it is easily verified that LU equals to the L matrix multiplied by the upper triangular matrix U. That's going to give you A. So the matrix L in the previous example is a lower triangular matrix with 1 on the diagonals. we say that L is unit lower triangular. The factorization of the matrix A into a product of a unit lower triangular matrix L times a strictly upper triangular matrix U is often referred to as the LU factorization. So the three row operations that were applied to the matrix A can also be represented in terms of multiplications of elementary matrices E1. So you have your matrix A here, you have a E1 matrix, E2 matrix, and then E3 matrix. So each steps of the multiplication can be represented in terms of multiplication. Yeah, it can be represented in terms of a elementary matrix. So the first operation that we did was to so we can represent in terms of elementary matrices. We did negative one half row one plus row two, and here we have negative one half. So let me do it on paper. So now the raw operations. So these operations, I will go now to represent them in terms of a matrix. So if we take the identity matrix, if we're looking at the first operation over here, we can take the first operation will be in a matrix called E1, E sub 1. And that E sub 1 is actually identity matrix like this one, 0, 0, 1, 0, 0, 0, 1. And we apply that row to it, negative 1 half plus row 2. So negative 1 half row 1 plus row 2. And that's going to be equal to this new matrix E1.
Sir, we can
Yes,
see well what is on the upper paper. Yeah, thank you, sir.
okay. So so I was saying that you take your identity matrix, and when you have your identity matrix, you want to transform it into uh, a elementary matrix. Now, my goal is to transform it into. I want to replicate these elementary row operation. I want to write their matrix version. So, in order for me to write them in terms of a matrix version, I have to start with the identity matrix. And from the identity matrix, I reapply these operations to obtain the matrix E1, the elementary matrix associated with this row operation. So here I'm going to have the matrix E1 that is stemming from the identity matrix to whom we've applied this row operation. And we're going to obtain the following matrix here, negative 1 half. Okay. The E2, so the second operation that we applied was to actually take the identity matrix and to the identity matrix we apply this operation, negative 2 row 1 plus row 3. We are going to obtain this elementary matrix. And then a negative 2. Negative 2. Okay. Now the third operation was I have my identity matrix, and I'm going to apply to this identity matrix 3 times row 2 plus row 3. That's what I'm going to apply now to the identity matrix. 3 times row 2 Yeah, 3 times row 2 plus row 3, and I'm going to obtain E3. This is the third operation. Notice that we don't write 1, 2, 3 like that. No. E sub 1 is actually meaning that this is the first operation that we conducted. E2 means the second operation. E3 means the third operation. So the third matrix is going to be 1, 0, 0, 0, 1, here, 1, here, 0, 0. This is my E3. Okay. So for me to go from A to the like to obtain the upper. Okay, this was my upper, my U over here. This is U. U is this matrix here. 2 4 2 3 0 1. This is my U matrix. So to go from A to U, we apply a set of row operations. Let me write it down. I have my A matrix here. I have my matrix A. So on matrix A, what I've done, I've applied row operation 1, this one over here. But in terms of matrix, it's E1, E sub 1. And after applying E sub 1, I've applied to this group, this second operation, E2. In terms of matrices, is this one, E2. So I start with A, and I left multiply A by this one. And after that, I left multiply A by E2. And after that, I'm going to do the third operation on E, which is E3. And finally, this product leads me to the upper matrix U that is over here. So if it was in terms of matrix multiplication notation, it is this way. So I take my matrix A, left multiply. I know that left multiplication will affect the rows, 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 and I obtain this U matrix, which is this one. Now, this is like the first one. Now, the second one will be to determine, so using this, so this is what we've obtained. So from this one, we can obtain a relationship. There is a relationship that we can obtain out of this. I know that this is one product. This is a product of matrices. So I can group these E1, E2, E3 together. And what I'm going to do is to multiply. I know that they are invertible, so their inverse exists. So we know that E1, the elementary matrices are non-singular, so that means that they are invertible. And if they are invertible, their inverse exists. And if their inverse, so if their inverse exists, and also it's a product of non-singular matrices, and the product of non-singular matrices is non-singular. So I can write this because they are non-singular. Inverse equals to A, but because I have left multiply this side of the equation by this expression, I have to do the same thing on the other side of the expression. Inverse multiplied by U. I'm looking for a relationship between another relationship between A and U. This is one relationship between A and U. Let's look at another relationship. So this one and that one, they're going to cancel. And I'm going to get A over here. And remember, if I had A B inverse, I can write it as B inverse A inverse. Now if I have this product inverse, it's going to change the order. It's going to be the product of them, but in reverse order. So it's going to be E3, no, it's going to be E1 inverse, E1. So E1 comes first, inverse, E2 stay at its place, inverse, and then E3 inverse. multiplied by the upper triangular matrix. So from the upper triangular matrix, we can obtain A by multiplying it by the inverse of those row operations. So let me write it again. Like E1, this one E1 is gonna be, let me write it over here. E1 inverse, E2 inverse, E2 inverse, E3 inverse time U equals to the matrix A. Now, if I take, let me write E1 inverse. If I was calculating the inverse of A, of E1, I would obtain the same thing. E1 is negative here, but if I calculate its inverse, I'm going to have plus 1/2 over here. So it changes the sign. If I was calculating the inverse of E2, it will change the sign to positive here. If I was calculating the inverse of E3, it will change the sign of E3. And if I do E1 inverse times E2 inverse times E inverse, these like E1 inverse, E2 inverse, E3 inverse, E1, E2, and then E3, this is going to be equal to L. That's going to be L times U. That's going to be equal to A. Okay, so if I do E1 inverse, 1 times 1/2 here, 0, 0, 1, time E2 inverse, which is this one, time E3 inverse, E3 inverse, which is 0, 0, 0, 0, 1, negative 3, and 0, 0, 1. That will be equal to the L matrix, which was 1/2, 2, negative 3, and 1, 1, 0, 0, 0, 0. Okay, so if I was doing the product of these three, if I was doing the product of these three, I would obtain the L from the L triangle. So in other words, we can conclude from this that L equals to E1 inverse, E2 inverse, and then E3 inverse, and then E3 inverse. So this is just to establish. So let me summarize the relationship between A, U, and L. So this is so A. We've seen that A was equal to. Well, we've seen that E2, E3, E2, E1, A was equal to the upper triangular matrix U. We also seen that this one relationship. The other relationship is that A equals to E1 inverse, E2 inverse, and then E3 inverse multiplied by U. The other relationship was L is equal to E1 inverse, E2 inverse, and then E3 inverse. We also seen that A is equal to L times U. Okay, so these are all the relationship that, based on the problem that we have, we can use any one of those. Okay, but this also shows that to obtain like L and U are actually related to one another by elementary matrices. So let's go back to the note. So any questions related to that? Okay. Okay, so these are the relationship that we can deduce from this. Let's go back to the note. So since the elementary matrices are non-singular, we can multiply e to e3, e to e1 by their inverses, and we have e3 into e1 inverse equals to e1 inverse, e2 inverse, e3 inverse. Plus the matrix A is going to be equal to e1 inverse, e2 inverse, e3 inverse multiplied by the upper triangular matrix U. Now, so e1 inverse times e2 inverse times e3 inverse is going to be equal to this multiplied by that multiplied by this, which is equal to the L function, to the L matrix. So in general, a n by n matrix A can be reduced to a strict upper triangular form using only row operation 3. Then A has a LU factorization. The matrix L is unit lower triangular. If I is greater than j, then L sub ij is the multiple of the jth row subtracted from the ith row during the reduction process. So now we're done with that. So normally homework section 1 5, number 1 through 32, page 84 to 86. Okay, so now let's talk about partition matrix. So if we have matrices, we can partition them. Like if there are a lot of entries, we can partition them by using horizontal line or vertical lines. So let me show you that. So any questions before we move on to partition matrix? Okay. So you can, let's say you have like a big matrix like this one. Let's say you have a matrix C with entries 1, 2, 3, and then 4, -2, 1, 3, and then 6, 4, 1, 2, and then 2, 1, 1, -1, and then 2, 3, 1, 2, and then 4. Let's say you have a giant matrix like this one. You want to partition this matrix. What you can do to partition them is to actually construct, use like a horizontal line like this one, and then a vertical line like this one. Or that's one way of partitioning it. So now this is one matrix, this is another matrix, this is a matrix, and this is another matrix. So we partition this giant matrix into 4 parts, right? Now this part we're going to name it C sub 1 1. Okay, so the it's like a new matrix. This one is going to be called C sub 1 2. So first row, second column, the matrix C sub second row, and then first column. And this one over here is going to be C sub 2 2. So in other words, it's as if you had a matrix C like this, a matrix C like this with entries C sub 1 1, C sub 1 2, and C sub 2 1, C sub CO2. So this new version of the matrix is what we call the partition the matrix. This is one way we could have partitioned anyhow. It could have been we could have partitioned this way. Let me show you another way of partitioning it. The same matrix, we could have written something like this. Matrix C, 3, 4, negative 2, 1, 3, 6, 4, 1, 2, 2, 1, 1, negative 1, 2, 3, 1, 2, 4. I could have done something like this. Partition this way. That's it. This is my C11, C12, C 21, and C22. I could have partitioned this way. So I could have used the partition any hour I want. I could have put the vertical line here, here, or here. Now I put the horizontal line here. So yeah, depending on the situation that you have, you find out what is the best way of partitioning it. But yes, so this illustrates the concept of partition. And the C11 matrix that we have here, C11, is actually this matrix here, C11, which is 1, 2, negative 2, 1, 4, 1. This is your C11. And C12 is your matrix over here. C12 gonna be 1, 3, 1, 1. That's your C12. We could have also partitioned using columns only. So for instance, let's say that I have a matrix. Let's look at a matrix B, for example. Let's say I have a matrix B. I can partition my B matrix with entries this. I could have partitioned my B matrix only with by the rows, by the columns, or I could have partitioned also B on the row side. So I have negative 1, 2, 1, 2, 3, 1, 1, 4, 1. I could have partitioned it this way. Okay. So this partition B will be written as B in terms of B1 that represent one column vector B2, and then B3 as one column vector. Or this one in terms of row vector, I will have written as uh, B1, B2, and then B3 like this. Okay. So this technique is basically called the partition. Sometimes when there are too many things to multiply, too many entries, you can try to partition your matrix to actually do the multiplication to save some time. Let's go back to the note. So any questions regarding the partition of the matrix?
No, sir.
Okay, let's go back to the note. So 1, 6 partition matrices. So a matrix C, it can be partitioned into smaller matrices by drawing horizontal lines between the rows and the vertical lines between the columns. The smaller matrices are often referred to as block. So for example, C equals to this giant matrix. If lines are drawn between the second and the third row and the third rows and between the third and the fourth columns, then C will be divided into 4 submatrices: C sub 1 1, C sub 1 2, C sub 1 2 1, C sub 2 2. So C sub 1 1 is a block, C sub 1 2 is a block, and so on. So this one here is a block, this one is a block, this one is a block, this one is a block, just like C11 block. So one useful way of partitioning a matrix is to partition it into columns. So for example, B equals to this matrix over here, negative 1, 2, and 1, 2, 3, 4, 1, 1, 1. You can partition B into 3 column submatrices. So you have B equals to B1, B2, B3. You have this matrix over here. Okay. So any questions related to that? Now the next one, um, the next one. So let's assume that you have a. So in the this is the previous example that we've done. We have a matrix B. Now suppose that we are given a matrix A with three columns, and then the product. So the product A times B can be viewed as a block multiplication. So each block of B is multiplied by A, and the result is a matrix with three blocks. So it's like if you have, for example, to do A times B, you can consider like your B matrix as a block. You can partition it by columns into column vectors B1, B2, and then B3, and then you multiply your matrix A by each block. So A times B1, A times B2, and then A times B3. So we can see an example of that. So if, for example, if A is equal to this matrix and B is equal to this other matrix, calculate AB by finding AB1, AB2, and then AB3. So let's try to solve this one. So you have a so we went by the formula. We had AB like this, A B, and from AB we've decided, okay, we're going to partition B into column vectors B1, B2, and then B3 like this. And then if we do the multiplication, we can write the multiplication of these as AB1 like this, AB2, and then AB3. So let's calculate AB1, AB2, and then AB3. So AB1 is equal to the matrix A. A is given. A is actually 1, 3, 1, 2, 1, negative 2. So AB1, 1, 2, 3, 1 here, 1, negative 2. B1. B1 is going to be, this is my B matrix over here. B is going to be equals to, in terms of column vectors, and B is going to be actually negative 1, 2, and 1, 2, 3, 4, 1, 1, 1. And I am actually blocking, creating blocks like this. So this is going to be my B1, this is going to be my B2, and this is going to be my B3. So B1 is going to be this block over here. Negative 1, 2, and then 1. By the way, I can do the regular multiplication this time, this, but I'm using a different technique to do the multiplication. So now I'm taking this row, multiplied by this column, and I insert it into the row, and this row times this column, the scalar product of these. So it's going to be 1 times negative 1 here, plus 3 times 2, plus 1 times 1, and then this row now times this column. So 2 times 1, 2 times negative 1, plus 1 times 2, plus negative 2 times 1. And if I do the calculation, I have negative 1 plus 6 plus 1, negative 2 plus 2 minus 2. And that's going to be equal to 6, negative 2. That's the first block. So the first block that I'm going to insert over here. AB2, let's find AB2. It's going to be equal to 1, 2, 3, 1, 1, negative 2 times negative. Now the second block is 2, 3, 4. So 2 times 3 times 4. Do the multiplication. If I do the multiplication just like I did with the first one, I'll obtain 15 and then negative 1. Now AB3, if I do the multiplication, I get 5 and 1. Now A times B, which is equal to the matrix A multiplied by the blocked versions of B, is going to be equal to uh, the following: 6, negative 2, 15, negative 1, 5, and 1. Because I did the partition around I did a partition on the columns, my result also can have as results columns over here to indicate that I partition my B matrix. That's, or you can simply write the answer without the partition, but you can also write it this way. So from this we can generalize. Let's say that you have a, so any questions on this example? So from this we can generalize. Let's say that you have a matrix A which is M by N, and you have a matrix B which is N by R. So the matrix B can be partitioned into B sub 1 all the way to B sub R. And then you have, if you want, you can do a block multiplication of A times B, and that's going to give you the matrix A times the vector B1, matrix A times the vector B2, column vector B2, dot dot dot, matrix A times the column BR. Okay. So yes, so that's the general, in general the rule is if you have a matrix A, you have B which is a partition matrix, you can do the product of those, and you have another, you can do block multiplication and you have a new matrix. So for example, let's say that you have a matrix A. um, okay, no problem. So this example is not that relevant. Let's move on to the next point. So let me go back to the notes. Okay, so in general, if A is a M by N matrix and B is a N by R matrix that has been partitioned into columns B1 dot 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 BR, then the block multiplication of A times B is given by A times B1, A times B2 dot 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 A times BR. In particular, A sub 1, 1, A sub 1, A sub 2, A sub n is equal to the matrix A. Now the matrix A multiplied by the identity matrix. Remember, the first column of the identity matrix is called E sub 1. E sub 2 is the second column of the identity matrix. So it has if you had a matrix A and you are partitioned the identity matrix. And then the identity matrix is made multiply, you multiply your matrix A by E1, the first column of your identity matrix, A times E2 all the way to En. Okay, so that's a particular case of that generality that we have. Now the next is, let A be a M by N matrix. We can partition A into rows. So now previously we've partitioned a matrix by its column. Now we can partition it into in terms of rows. So if we partition A into rows, then we have A equals to E1, no, vector A1, A2, all the way to AM. Now, if B is a N by R matrix, the IF row of the product A times B is given by AI multiplied by B. Now we can generalize that the product AB can be partitioned as follows. A times B is the vector A1 times the matrix B, A2 times the matrix B all the way to B, AM times B, matrix B. So let's see an example of that. You have a matrix A times B. Now you have A equaling to this matrix and B equaling to this matrix. Now you want to calculate AB using this formula. There are many ways you can partition B if you want to, but now we want to partition A by remove by the rows. So we can use this formula. So let's try to do this one. Let's try to solve this one. You have a matrix A. We said that we can partition a product AB like this. You can partition into A1, the row vector A1 multiplied by the matrix B, the row vector A2 multiplied by the matrix B dot 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 A M times the matrix B. So A in this particular case is actually equaling to 2, 5, 3, 4, 1, 7. I can partition it by rows, and B is this matrix here: 3, negative 1, 2, 1, negative 3, and then 1. So let's try to find this one here, the vector A1, the row vector A1 times B. So A1 multiplied by B is going to be this one over here. This is my A1 to 5 to 5 multiplied by 3, negative 1, 2, 1, negative 3, and then 1. And that's going to be equal to, so the row time column, row time column, row time column. So 2 times 3 plus 5 times negative 1. Now next row time column. So 2 times 2, 2 times 2 plus 5 times 1. Finally, we have here 2 times negative 3. So these 2 times negative 3 plus 5 times 1. So 5. So if we do the calculation, we'll obtain 1 for the second number, 9. Last one is negative 1. And that is my A vector A1 multiplied by B. The second one, the vector A multiplied by B is going to be equals to this vector here, 3, 4, times the matrix B, which is here, 3, negative 1, 2, 1, negative 3, and then 1. You multiply, you have 3, 3 plus 4, negative 1, 3, 3 times 2 plus 4 times 1, and negative 3 times negative 3 plus 4 times 1. When you do the calculation, you'll obtain 5, 10, and a negative 5. So if you do the same thing so this is A2, the row vector A2 multiplied by the column by the matrix B. Now the third one, A3B equals to negative 4, 9, and then 4. Now as a conclusion, so we have now this vector, uh, this one, and that one. So we can conclude now. AB, which is equal to the vector A1, B, A2, B, and then A3, B is going to be equal to this row vector here, and then this, and I'm going to superpose it to this vector and then that vector. So that's going to be 1, 9, and -1, 5, 10, and -5, and -4, 9, and then 4. So we have seen that in this particular section that to do the multiplication of matrices, you can break your matrices down if you in terms of blocks. You can create blocks by separating the columns, or you can do the same thing by separating the rows, or you can use a combination of row column to separate to create blocks. So any questions related to this? So I'm going to take attendance. If not, we're going to stop here for today. Okay, hold on. It's coming. Okay, just be patient a little bit. It will come. Okay. So okay. Okay. Aka Cyril. Mr. Aka Cyril. I think Aka. I think okay, it's present. It says the internet is slow. No problem. Ako.
Present, sir.
Present,
Aleppo.
sir.
Okay. Koulibaly. Eile.
Present, sir.
Fofana.
Present, sir.
Hassan. Hassan. Okay. Lai.
Present, sir.
Lai.
Present, sir.
Ouattara Idriss.
Present, sir.
Ah.
Present, sir.
Touré Nour. Touré Nour. Mr. Touré Nour. Touré Sheikh.
Present, sir.
Touré Sheikh is here. And Touré Malaika.
Sir, present.
Okay, so Touré Nour says present, so no problem. Okay. All right, so with that being said, I will see you on Wednesday. And take good care of yourself.
Thank
And
you,
I'll
sir.
wish you the best of luck for your other classes.
Okay, sir. Excuse me, sir.
Yes,
About the finals.
yes.